Someone came up to me who had a problem where he was trying to reduce the number of things that he had to show a user for time series data. And they had entirely too many curves for that person to effectively make sense of it. And in order to reduce it, he was finding the similarities between these curves. In order to have an effective reduction, he had to reduce very many curves, and they had very long histories. So when he did this with SQL, it was very inefficient, and the SQL was actually fairly complicated for what it was doing. When he rewrote it in Python, it was incredibly slow, and we needed to figure out how to improve the efficiency.
So, when you say SQL is slow, what do you mean by that, and how can we solve that?
Okay, so SQL it's not doing, it's not, SQL is not slow for this case. It's a very inefficient method of solving this kind of problem. So instead of doing joins and lookups and indices, we know that these time series are all going to line up. So it just makes more sense to keep them in sequence and zip them together rather than trying to join. Um, and when he had converted this code from SQL to Python, a lot of that was already implied, which is already a great benefit. That the speed of this query had already gotten to 6 seconds from an unbelievable, 6 minutes from an unbelievable amount of time before then. But there's still a long way we can go. So I boiled this problem down to its essence here, which is simply a group of time series information that essentially constitutes a matrix. So we have many curves, and for our example here, I'll show 1,000. And each one of them have a certain number of history samples associated with them, which is also 1,000. And we want to find for every one of these curves their most similar neighbor. And in doing that, we just took the sum of squared error against each of their neighbors, and then take the most similar neighbor from those. It's pretty simple, but it can be the beginning of a fairly good algorithm. So when you first write this out in Python, the simplest way is simply to place all of those into a list of lists, and then take two lists, compare them, and find out how similar they were, and then repeat it for every possible pair of lists. And once you have that structure, you find the least difference and associate it with each curve.
Why do we want the least difference associated with each curve?
Because in this case, we're using it for agglomerative clustering. So we're simply saying that you can zoom up or down this tree of clusters and find this cluster family, and or this section of this group of curves, and each of their most representative curves, and for each one of them, each of their most representative curves, and so on. So that way, people can choose, if they think that this curve is interesting, they can go find out subdivisions or families or subfamilies of that curve.
So, let's say if I have 1,000 curve, what do you mean by finding the most interesting curves? Is I want to reduce the amount to maybe only 10, and I've come up with a way to efficiently reduce what we have to look at to 10.
So 10 is kind of arbitrary here, but we do want to show the user very few curves to begin with, because we'd like to show them all in one screen. So 10 is a reasonable number to fit on a screen in most cases, and we'll show them the 10, uh, I guess you could say, most different curves, and for each one of those 10, the curves that are most similar to them. So that way you only need to see about 10 on a screen at a time.
So, Sean, when you solved this problem, you said that Python in doing list of lists is inefficient. Why is that?
So the memory storage is not very local. It's not going to be contiguous. And each list will contain lists that contain objects that contain integers, and so you have pointers to pointers to pointers to pointers, and they're actually scattered all around memory. Now, they may actually be closer to each other than you might think. They might be in the same megabyte or something, but they're not contiguous. They're going to be bouncing all around.
Wait. What? While you go on, let me stop you. What is contiguous?
Oh, so typically, for data that you are using together, you would like to keep it together. That way, for cache locality, which is to say when it's pulling it from the memory into your processor, it takes it in contiguous blocks, which is blocks that are together, uh, which is one segment of memory. Typically, there's something like 4,000 bytes, for example. And when it reads those 4,000 bytes, it only ever reads always 4,000 bytes. So you might as well make as much of that useful bytes as possible. And in these lists of lists, that's not what's happening. You're getting a few bytes here and a few bytes there that you actually wanted, but you're actually bringing in a bunch of trash from memory at the same time. Now, you might have higher levels of caches and everything that are trying to make this less of a problem, but underlying that's the problem you're causing by keeping your data scattered in memory. This is not wrong. It's just a fact that Python is trying to be flexible, but your algorithm is very static. And so you can do better for this algorithm.
So, what are some other things in using it as a list that makes Python a little slower than what we're going to talk about?
So these lists, they're discontiguous, they're dynamically typed, but NumPy is not going to be either of those things. It has a single list and an interesting way of iterating through them. And that single list has to have a defined size, and it has to have a size for every element inside it. And so as a result, it can keep everything together because the location is just a matter of multiplying and adding.
Coming back to this, how does vectorization help us?
So, like I was saying, you are getting 4,000 bytes from memory, at least from RAM usually. And you'd like to do as much as you can with that at a time. Um, so vectorizing allows you to bring all of that data together and then run operations on all of the elements of that array at the same time. Um, and it keeps going further down in the process. So when it comes in from memory, you're going to use all of that data. But then later on, uh, processors have been improved so that they can operate on multiple elements in that vector at the same time, as long as they know what the type is and the fact that it's aligned. And these things are all possible because we know exactly where it's going to be, and you can simply have multiple adders all lined up to run on separate elements in that same cache line at the same time. Um, and even so, the pipelines keep getting better for the fact that now if you want to multiply and add at the same time, you can even do that in one cycle. And so people, they really underestimate the amount of performance they can get out of their computer because they're not architecting their problem in a way that the hardware can accelerate.
Thanks for watching. If you like this video, please press the subscribe button, and we will see you next time.